Okay, ready to get started? How is your homework going? I noticed just now that I've got some discussion board posts to respond to, so I will I'll get to that as soon as I can, hopefully after class here. But how is it going generally? The homework. Any big questions? So I'll reply to the discussion board questions as soon as I can. My plan for today is to finish up topic 2 for us. And so I think where we left off was right around here. This is topic 2.pdf, slide 28. We've talked about what vectors are, matrices. For a matrix and a vector, we've seen basic operations like addition, multiplication. We've seen basic characteristics of a matrix like square versus not square, orthogonal. We know the identity matrix. We know the inverse of a matrix. And then last time we saw eigenvalues and eigenvectors. And so this is talking about a square matrix, A. And I mentioned last time that we're going to be especially interested in square matrices because a covariance matrix is a square matrix. And we're going to do a lot with covariance matrices. So a square matrix A, we can kind of decompose it into component chunks, where those chunks, those components are represented by a scalar and a vector. The scalar is called the eigenvalue, and the vector is called the eigenvector. The definition is this one, that you can take the matrix A and multiply it by the vector x, and that's the same vector as if you just multiplied the vector x by lambda. It's a special relationship between lambda and x in order for us to make that simplifying representation of A. We've kind of replaced A with a scalar. In R and any or at least most software packages, you can get eigenvalue, eigenvector pairs. If you provide the square matrix, you just call the right function and it gives you back to you. So in R, for example, I'll show you how to get the Eigen Decomposition of a matrix, and it gives you back, here is a vector of lambdas, and then here's a matrix of eigenvectors. If A is a P by P matrix, if there's P variables in our multivariate data set, then the covariance matrix will be P by P. And when you decompose a P by P matrix, you get back P eigenvalue, eigenvector pairs. So it's like you're taking the whole matrix and you're breaking it up into component pieces, and you're going to have exactly P pieces. Those pieces are organized such that the first one tells you the most about the original entity of all of them. And then the next one explains the next amount, and so on. So they're ordered in how much information they represent. So in R, when you say, give me the Eigen Decomposition of this square P by P matrix, it's going to give you back a vector that contains all the lambdas, all P of them. And then the P eigenvectors will be put together in a matrix. So it'll be again a P by P matrix where the eigenvectors are in the columns. I'll show you that with a real data set momentarily. But just to make it clear in your head, when we're doing Eigen Decomposition, we're getting back one for every variable and eigenvalue, eigenvector pair. Those eigenvectors in R and in most software are going to be standardized. When they're displayed to you, A vector is just a collection of numbers organized in a column. And there's many choices of the specific numbers for each eigenvector for it to still be an eigenvector. So there's a non-determinacy issue with this decomposition stuff. So by convention, what's usually returned to you as the eigenvector is a standardized or normalized version of it. A normalized vector typically means that we've rescaled it so that its length is 1. So when we get back the eigen decomposition of a matrix, the eigenvectors themselves, which will be columns of a matrix that's given to us, will have inner product equal to 1. That's the same thing as length of 1. Several slides back we defined what the length of a vector is. Basically, it's the square root of the inner product of it with itself. So these are normalized versions of eigenvectors. And typically, we'll refer to a normalized version of an eigenvector as E. That's the notation we will use. So in the notes that follow, when we continue over and over again to talk about eigenvalues and eigenvectors, I'll use this kind of notation. The first, we have one pair for every variable, and the first pair is given by lambda 1, E1. Lambda 1 is the eigenvalue, E1 is the standardized eigenvector. Here's a very simple example. I ask you in the homework to take a really simple example and figure out what are the eigenvalues and the eigenvectors. Then you can verify them like is done here. Just simple plugging in to the equations. A more general way to find eigenvalues, eigenvectors. Suppose you have a matrix A. It's P by P. And you want to know what the eigen decomposition is. The easy answer is just to go to R and call the eigenfunction. But mathematically, what is it doing? One way to discover the eigenvalues is by solving this equation. It's called the characteristic equation. Just FYI, I'm not going to test you on that. But behind the scenes, when your computer goes and gets eigenvalue, eigenvectors, it's solving a mathematical equation. This equation, the solutions give you the eigenvalues. And once you know the eigenvalues, you can get the eigenvectors by algebra. One thing about eigenvalues and eigenvectors that I want to make sure we've seen is that the actual signs of the eigenvector coefficients are arbitrary. So, for example, you might use R to do a eigenvector decomposition, and you get as your first eigenvector the number 1.2 and then the number negative 1.2. And suppose I use SAS or another program or MATLAB, and with the same exact matrix, I ask for eigen decomposition, and it gives me minus 1.2, 1.2. So the sign, it's like yours is mine after multiplying by negative 1. It turns out that you can multiply the coefficients of the eigenvectors by negative 1, and it doesn't affect the meaning that we'll get from them. So just tuck that away in the back of your mind. I'll revisit that, and I'll show you some pictures that make it clear. But it may be as you're doing your homework, hey, I ran the function and I got these numbers, and somebody next to you ran it and got the same numbers but negative 1. That's not an error or anything. Okay, one immediate corollary, I guess, of the eigenvalue, eigenvector definition. If we have eigenvalue, eigenvectors that we've already figured out for a symmetric matrix A, then there's what's called the spectral decomposition theorem that is intuitively useful and practically useful as well. So if you take a symmetric matrix A and you decompose it, into P eigenvalue eigenvector pairs, then you can re-express the matrix A as this on the right side. I can rewrite A as a piece that involves the first eigenvalue eigenvector plus another piece that involves the second plus dot dot dot. The eigenvalue eigenvectors have been ordered, remember, such that the first one explains the most of what makes A tick, and then the second one explains the next most, and so on. Suppose A represents a 40 megabyte digital image that you took of your cat, like we talked about last time. If you decompose that matrix of pixel intensities into eigenvalue eigenvectors, then you could take just the first so many chunks of this spectral decomposition and result in a picture that looks essentially the same, but it's been compressed. Some of its finer details have been removed. One of the things that is intuitively good to get about what eigenvalue eigenvectors are doing is that once you know them, you can express the original matrix, like a covariance matrix or a correlation matrix, as this sum. That immediately leads to, if you want to replace that matrix, the original matrix, with kind of a compressed version of it, then a sensible way to do it would be to start with the first chunk, the first eigenvalue eigenvector. And then if you need more detail, add the second one, and then add the third one if necessary. But you chop off and ignore the remaining ones. This expression is like I think of it as like an image compression example. You take an initial image A, you decompose it like this, and one way to compress it that's sensible would be to take just the first few chunks of eigenvalue eigenvector contributions. Let's power through this. I need to cover this stuff before we go to doing actual statistics. So I want you to know what the eigenvalue eigenvectors are. You'll make use, I think, once in the class of the spectral decomposition theorem, but I'm not going to test you on it. I do want you to know what quadratic forms are and what positive definiteness is. These look like abstract mathematical statements, but they translate directly to multivariate statistics. Excuse me. So what's a quadratic form? If you have a vector x and a square matrix A, and you do that type of expression, x transpose AX, that's called, gets a special name, a quadratic form. The reason it's called a quadratic form is you're kind of taking a vector x and multiplying it by A, but x is there twice, so it's kind of like you're doing A times x squared. Doesn't really make sense. I'm talking kind of rough there, but in a vector sense, x is there twice. In fact, if you wrote this out, suppose x is two-dimensional. So there's an x1 and there's an x2. There's only two variables. Then x transpose AX would look like this. X transpose is that 2 vector that's been transposed, so now it's oriented horizontally. The A matrix is P by P, or 2 by 2 here. And this is just definition of its entries. First row, first column, first row, second column, and so on. And then here's X again. So matrix multiplication of this would say do x1 times a11 plus x2 times a12. And then multiply that by x1. And then you do this times that and multiply by x2 and you add them all together. So matrix multiplication gives a quadratic form, or a quadratic equation. Quadratic in the variables x. The reason you care about, or I want you to care about these quadratic forms, is because the statistical distance is a quadratic form. Remember that something that I've mentioned a couple of times now and that I promise will be a part of our class throughout, the statistical distance. For example, the distance between a random vector x and its mean vector mu is square root of x minus mu transpose covariance matrix inverse x minus mu. So let me write that a little differently so it's cleaner. D squared, if I don't take the square root, the squared distance is just that expression. So that's another way of saying this. A transpose, or let's do B transpose A inverse B. That's a quadratic form. That statistical distance, much of what we do, like cluster analysis in particular, is all about distances. If I'm clustering, I'm grouping individuals together who have similar patterns across the variables. So in order to put things together that are like each other, I need a way of quantifying how alike you are with another individual. Or conversely, how different you are. What's the distance between the two? Statistical distance comes into play there. Statistical distance, this quantity is right in the middle of the definition of the multivariate normal PDF. In your homework, you need to code up the multivariate normal. And in the exponent of its PDF is that expression. So we care about quadratic forms. And we need to have, for the theory of our methodologies to hold, in most cases we need our quadratic forms to be called positive definite. So there's two definitions down here. This is just a generic version, or a generic way of saying quadratic form. And a characteristic of the matrix A is that it can be non-negative definite. It's non-negative definite if, for every x out there, when you make the quadratic form, it's non-negative, bigger than or equal to 0. And similarly, if A is such that for any old x, this quadratic form is strictly bigger than 0, then A is called positive definite. So it's kind of like A is a matrix, a scaling matrix, typically a covariance matrix or an inverse of it, that will always give sensible distances. They won't equal 0 and they won't be negative. So there's quadratic forms. Among quadratic forms, a special type is called positive definite. Let's get that. This essentially says what I was just saying a second ago about why we care about quadratic forms. It's related to distance. It's also related to the multivariate normal. We will have to slog through this slide for one homework problem. It's lots of mess, but let me tell you what the idea is, at least. Let me come over here. So suppose we have two-dimensional data, x1, x2. So only two dimensions. And suppose the mean, mu, is equal to 1, 1. And suppose we have some covariance matrix. It's 2 by 2 covariance matrix. So it's the variance of variable 1 and variance of variable 2 on the diagonals, and then covariances in the off diagonals. When it comes time to do things like confidence intervals, a confidence interval is go estimate a mean and do plus or minus to endpoints such that you can say I'm 95% confident that the truth is in there. So one of the things we're going to do in a multivariate sense, we're going to want multivariate confidence intervals. We'll call them confidence regions. And so I would like to, for a given level of confidence, 95% or 80%, whatever, I would like to go out and just far enough in all directions to somehow capture 95% confidence. So the slide that I showed briefly is all about how do you, given a random vector that has a mean vector and a covariance matrix, how do you go out 95% in all directions simultaneously? One of the complications is that there, in this picture, there's less variability in the vertical direction for variable 2 as there is in the other direction for variable 1. There's different variances between x1 and x2. So the cloud of 95% confidence will tend to be tighter for x2 because it doesn't vary as much. And then the rotation, the fact that they're rotated and following each other along an angle, suggests correlation between x1 and x2. All that to say, the appropriate way to start at a mean vector and go out simultaneously in all directions a particular value is a function of statistical distance. So to find, and by the way, if you start at a mean vector, like mu in this case, and you go out in all directions in such a way that it's rotated and there's different variability along the two major axes, what fundamental shape is going to characterize or outline the region I'm about to find? That blue shape from your geometry or whatever, you'd call it an ellipse. So we're going to be looking for an ellipse that is a constant statistical distance from the mean. All right, I won't dwell on that right now. We will come back to this, but the idea is that, or an important player in this relationship, find the ellipse or the ellipsoid region that's a constant distance away from the mean. That's how we're going to get confidence regions. Give me a 95% confidence region for my 5 variables simultaneously. The angle at which the axes are rotated, the magnitude of those axes in each direction is going to be all about eigenvalues, eigenvectors. So we'll return to that. I do have a homework problem that asks you to basically find the ellipse of constant distance away that corresponds to a X% confidence interval. All right, before we run out of time, I definitely want to say a little bit about random vectors. We did all that linear algebra stuff, vectors and matrices, basic operations, and so on, with this in mind, because data for our multivariate applications are vectors. If I have a collection of 1,000 US citizens who are eligible to vote, and for each one of them I'm going to measure 10 different things: their age, their height, their weight, their SAT score, bunch of things, P things. Then what I observe is I go around and sample from the population of all potential voters in the US. What I'm actually sampling is a vector. If I identify that person right there, for that person I'm going to write down P numbers, or P things. So my observation is of random vectors. This is where we kind of combine probability with the linear algebra basics to form a framework for talking about multivariate data. The first slide here is a review of what the univariate case looks like. We're in multivariate case, where for every individual I see a vector. Suppose instead it was for every individual I saw one number. Like for all those potential voters, I'm just going to write down average annual salary for the last 5 years. One number. That's univariate data. We could say that, pick a name like capital X. We could say that's a variable that's going to be my recording of average annual income for every individual I sample. That's a variable because its value will vary from individual to individual, and it's random in the sense that we're randomly picking people from the population. So by chance, we'll get some who make a lot and some who don't make as much. That's a random variable. For any random variable, there's a function that tells us how its probability is distributed. A random variable just means that it takes potentially different values, and the specific value it takes is subject to probability. The probability function is the function that tells you, you tell me the value, I'll tell you the probability. For every possible value, the probability function tells you what it is, what the probability is. It tells you the probabilities for all the possible values of x. So a couple of basic operations with probabilities. If x is a random variable, then its mean or expected value, let me back up real quick. We're talking for now about a discrete random variable. We could have a discrete or we could have a continuous. Discrete would be discrete possible values, like 1, 2, 3, 400 million, 400 million, and 1. For a discrete random variable, there's a probability function. It's called the probability mass function. If it was a continuous random variable, there's still a probability function, but it has a slightly different name. It's easiest to introduce the basics of expectation and variance and stuff with a discrete random variable. For a discrete random variable x that has a probability function p, the expected value, the average in a probabilistic sense, is defined as a sum over all x values of the possible x value times its probability. It's the sum of possibility times probability. If every possibility was equally likely, then that expression would be the straight average. Add up all the possible values, divide by the number of possible values. But it's defined more generally to allow for there to be differing levels of likelihood of seeing the different x values. So an expected value is kind of like an average, a weighted average of the possible values, where you're weighting with the probabilities. The variance of x, this you know, is a quantification of how spread out the random variable is. It is a variable, so it takes different values, and it's random, which means that there's like a distribution over which it takes values. So is that distribution over which the random variable takes values really wide, or is it really closely packed in on a particular value? That's a question of spread or variability. And the variance of x, probabilistically speaking, we call it sigma squared, and it also is just an expected value. It's a different one from the mean. It is the expected value, or the average typical value, of the squared difference between x and mu. If x tends to be very far away from mu, if a lot of the time it's way away from mu in either direction, then that squared difference is going to have lots of big values. And when you average all of them up, you'll end up with a big number overall for the variance. This expression is just, again, showing the mathematical expression for expected value. The expected value is like a weighted average. It's the sum over all possible x's, the possible values of what you're trying to compute an expected value for, times the probability that it is that particular value. So again, it's like a weighted average, weighting by probability. What's at the bottom with the calculus is just the extension to when x is continuous. Instead of averages, like add up and divide by a certain number, those are replaced with integrals. Integrals are like continuous versions of averages. But notice that it looks conceptually the same. It's like average, continuous version of average, of x weighted by its probability function. And the variance is like an average of the squared difference between x and mu, where the weighting is done by the probability function again. And then this is important for us. Suppose we have two random variables, x1 and x2. In our case, with just generally multivariate data, we have p random variables. So if you pick any two, we can talk about the covariance and the correlation between them. So here's the math. If x1 and x2 are two random variables and period. If they're two random variables, then there is a what's called joint probability function. Whereas the probability function from the previous slide, for every possible value of x, if you could plug that in and it would give you a probability. A joint probability function is going to give us probabilities for pairs in this case. You tell me the pair x1 and x2 and it will return to you a probability. Then the covariance between x1 and x2, the definition of that is, I think I showed you this last week or earlier this week, the covariance between two random variables is an expected product. And the product is of a difference, x1 compared to its mean, with the difference of x2 compared to its mean. Pretty sure I talked about this a little bit in the Q&A, so you might want to review that. But I talked about how what happens if x1 tends to vary together with x2. Like, for example, as x1 gets big, x2 tends to get big also. If that's the case, you're going to end up with a positive covariance. If you look at the multiplication there, if x is bigger than its mean, y is going to be, or x2 is going to tend to be bigger than its mean, in which case both of those differences are going to tend to be positive. So you'll tend to get big positive expected value. And conversely, if x being bigger than its mean tends to go with x2 being less than its mean, the product will be a negative number and you'll tend to get negative covariances. So the covariance is a quantification of how much these two variables vary together. And its sign tells us about the direction of the covariability. The correlation, something that we're arguably more familiar with, is just a scaled version of the covariance. Specifically, the correlation between x1 and x2 is just equal to the covariance between x1 and x2 divided by the standard deviation of the first variable times the standard deviation of the second variable. A covariance can live anywhere between minus infinity and infinity. Just like a variance can be anything up to infinity. A covariance can be negative infinity to infinity. But a correlation, because we kind of scale it or normalize it by dividing by these two standard deviations, is constrained to only go between -1 and 1. A correlation close to 1 suggests that if you were to plot x1 versus x2, you'd see a very tight scatter plot following the 45-degree line of equality. x1, it wouldn't have to be the line of equality, just any line. You would see a tight scatter plot following a line with a positive slope. Let's see what else we have to cover. Your homework has a little bit of this type of notation. So we will talk about mathematically data, multivariate data. What we observe in a multivariate data set, each individual gives rise to a random vector. So notation-wise, we could say for the potential U.S. voter number 122, the vector of 10 observations that I'm going to observe for him or her is x. So I can write it horizontally and not vertically and take up so much white space. Let's just call it x transpose, in which case it's x1, comma, x2, dot, 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 xp. That's a random vector. Then we can talk in terms of its expected value. Every random vector has a probability function, and therefore it has an expected value and potentially a variance. So this has expected value of x, where each component, it's a p vector, each component is just the expected value of that component, that variable. So e of x is just the vector of component means. Its variance covariance matrix. This is the capital sigma that we've already seen. We can also write that as covariance of x. And in terms of expected value, it's defined as the expected value of a product. The product is x minus mu transpose. That looks kind of similar to the statistical distance that we saw. Statistical distance, like the distance between x and mu, squared version, is x minus mu transpose sigma inverse x minus mu. What we just wrote down was that the covariance of a random vector x is the expected value of x minus mu transpose. So those two things kind of look similar, but there's a distinct difference. A distance, if you ask what is the distance between a particular x value and its mean, has to be a scalar. We don't compute vector distance. We're talking about a scalar distance, like Euclidean distance. The distance between this vector and that vector is 4, some number. So in this case, we have a 1 by p, because we've transposed the p vector, matrix multiplied by a p by p, and then all of that matrix multiplied by a p by 1. That's going to give rise to what we expect, a scalar, a 1 by 1. But the covariance of x, what we've called capital sigma, is p by p. So the expression looks a little bit different because the dimensions need to be just so. So this first product, or difference, is p by 1. And then it's multiplied by a 1 by p. If you multiply a p by 1 with a 1 by p, you get back a p by p. Notation is typically done this way. This is the kind of notation I'll use on the whiteboards and in the notes. That's just, let's blow up and show every element of the covariance matrix. Sigma 1, 1 is first row, first column. That's the variance of variable 1. And then down the diagonal, sigma 2, 2, sigma pp. Those are the variances of those variables. The off diagonals, sigma 1, 2 is the covariance between variables 1 and 2. The covariance between variable 1 and 2 is the same as that between variable 2 and variable 1. So these are actually written exactly the same because there is symmetry in this matrix. The correlation matrix, remember that a correlation is just a covariance divided by the product of the standard deviations. So the correlation of variable 1 with itself would be its covariance, which is actually its variance, divided by the product of its variance square rooted. That's just 1. The correlation of one variable with itself is 1. That should be intuitively clear. If you draw a histogram or a scatter plot of variable 1 versus variable 1, it's a perfect straight line. So by definition, the correlation matrix has 1s down the diagonal, and then the off diagonals are these correlations, numbers between -1 and 1. Okay, that's all the lecturing I'll do. In case you're mathematically inclined, I'll point out that at the very end of these slides is a couple of slides of important inequality and maximization results. So the Cauchy-Schwarz inequality, if you're going to go to graduate school, you'll see that for sure. The extended Cauchy-Schwarz is a slightly more general version. And then a couple of maximization lemmas that look gnarly, and it's hard to see how they could possibly have any application, but they'll pop up in your textbook in a couple of key places. When we're trying to solve a model, fit a model, how do I find the coefficients that best fit the data? Ultimately, that translates to maximize a quadratic form. And these results give us the answer there. Okay, I think I'll let you go. Rather than lecture more at you. Get the homework. So if you know how to do the homework, there's lots of stuff in these slides, right? I'm not going to test you on slide 41 if it was not in your homework. So if you haven't had practice doing it. So I would say, take as much of this in as you can. You can't possibly take it all in, I don't think, unless you're spending too much time on the class. So make sure you're good with the homeworks and any assignments that I give you, and that'll be the basis primarily for the exams. Okay. All right, thank you. Have a good weekend.
Can you do that first slot, the first drawing that has the statistical distance formula on it?
Say it again.
Can you do the statistical distance formula at the beginning of the class?
Here?
That one, yeah.
So the expected value, first of all, the expected value of a random vector is just the univariate expected value, univariate expected value. It's just component by component. And same thing with a matrix. The expected value is basically an average of every single component. So yeah, it's just you carry the integral into every row, every column. Hi.
Statistical distance formulation. You're saying that there is a constant statistical distance that is being calculated, but why is it taking ellipsoid form? Ellipsoid is having a different distance from the mean every time.
In Euclidean distance, it is. The statistical distance idea, by putting that weighting matrix in the middle, it allows for variable 1 to be more variable than variable 2, for example. So if the variation that you observe is that variable 1 is like this and variable 2 is like that, then a value that far away from the mean is not very unusual for x1, but it is for x2. So the statistical distance basically enforces that. This variable shouldn't be allowed to go as far because it doesn't vary as much.
But why do you say it is constant in that case?
Because a constant, it's constant in the statistical distance sense. Like this number right here is not very unusual for x1, but it would be very unusual for x2. We could say this value right here is just as exceptional as that value right there for x2. So the statistical distance is the calculation of that all the way around. That far is as exceptional as that far for the other variable.
Mean would be at the center of the
Yeah.